already seen in the videos with almost no math that we could redefine space and time and what kind of implications it had, And this video here is actually the same video with some additional very simple mathematics in order to show that we can derive, the special relativity rules without using the postulate of a constant speed of light. Great. Let's have a look again, at simultaneity as defined by Albert Einstein when he, explained to us the special relativity thing. Einstein's made some assumptions, as you remember from previous videos. In order to build our model, we need to start with some basic assumptions, and then from there we can derive everything else. Okay, almost everything else in the case of Einstein, and for that we need independent assumptions. So the first assumption was light or electromagnetic waves in general travels isotropically. What that means? Well, it means it's same thing in all directions, they will go same speed and whatever. And that's, remember, we need a reference. So relative to a Galilean frame of reference. A Galilean frame of reference is a frame of reference with no acceleration. If you need more details on that, you can go watch my other videos about special relativity mystery. It's a good one, with twins and triplets and everything. Wow, exciting. But anyway, that just means, it goes at, linear constant speed or doesn't move depending on which reference you take, but at least there's no acceleration. That's what a Galilean frame of reference means. Okay, so that's one first assumption. The next assumption was there's no privileged Galilean frame of reference. So in other words, you can take any frame of reference, provided it's Galilean, then you will be able to measure exactly using the same rules for to measure everything, okay? And you won't find a difference. Well, you will find difference maybe, but the rules will be the same. Constant speed of light. Okay, so that was one of the assumptions here, which actually caused problems to the physicists at that time, because they were measuring the speed of light, and whatever reference they would take as a frame of reference, they would find always the same speed, and we'll see why that is a problem. And finally, he defined time from that, because that was a whole goal, He defined time using clocks and simultaneity concepts. Okay, fine, that's what Einstein did. Now, the way it works for simultaneity, as you remember, you receive two events here, and then if they arrive at the same time, which means if you only see one event here, then you will say that those two space-time events are simultaneous, and then you use clocks, and then you can define time. So that was simultaneity according to Albert Einstein. Now let's try to, so that allowed to derive special relativity. Big deal, Mr. Einstein. Yeah, big deal. Anyway, the trick was that, if you use here the Earth as a frame of reference, and you see those two space-time events arriving simultaneously, well, it would not be the same if you change the frame of reference, even if it is a Galilean frame of reference, In this case, for instance, this space-time event would arrive before this space-time event here, because, the car has moved here. Therefore, that means that simultaneity depends on frame of reference, because on this frame of reference, these two events are simultaneous. In this frame of reference, this one arrives before this one. So there is not simultaneous. Interesting. And using that plus the fact that the speed of light from any frame of reference, Galilean frame of reference, was equal to a constant, led to the special relativity, by Einstein. Yeah, not bad. Okay. Now let's see what we can do from that. Again, we're going to take the same assumptions, light travels isotropically, no privileged Galilean frame of reference, the time defined using clock and simultaneity. No. First of all, we're going to remove this requirement, okay? Interesting. Quite a big deal. And also, instead of using clocks and simultaneity, we don't know what clocks means actually. We'll use space because we have defined what space is, and how we measure it. And therefore, we can do that now to define time. So how are we going to do that? Well, it's not very complicated, actually. Let's take an example. We use a car here, the blue car, which is of length b minus a, But if, to simplify things, we'll say a is equal to 0, therefore the length is equal to b. Okay. It's at rest viewed from the Earth. Okay, it doesn't move relative to the frame of reference here. Now, let's suppose that inside the car, there's a guy firing a bullet, that goes from A to B inside the car. Okay, like this, beam. Okay, now, simultaneously, and we know what that means because we have defined simultaneity before, simultaneously to the bullet, we send a light ray from A to D here, such that the light ray reaches D simultaneously, and again we know what that means, with the bullet reaching B here. So this looks like this. This is so fun. Okay, and then by definition, we'll say that the space-time event B, the space-time event bullet arriving at B occurs at time D, assuming A is equal to 0, and the time duration taken by the bullet to go from A to B is the spatial distance, here, equal to D. That will be our definition of time. So time in that case is actually a spatial distance, space distance. And we know what this is because we have defined space before. So that's quite interesting. The other thing interesting is if we look at the speed, of the bullet. Well, it would be like in classical physics, speed is equal to the distance, which was b, divided by what we call the time here, which is d. So the speed of the bullet in that case would be b over d. Okay, interesting. Now, the bullet speed viewed from the Earth is equal to b over d. That's what we just saw. The bullet speed viewed from the car, since the car is not moving, is the same, b over d. So it's equal to u1. Now, if instead of a bullet you send a light ray, then b is equal to d. Okay, so you get u1 is equal to b over b. And of course, u prime is also equal to b over b. That's equal to 1. So the speed of the light ray will always be the speed of a light ray from any Galilean frame of reference, which is equal to 1 in that case. Okay? Interesting. Okay, now let's see what happens if the car is moving. Okay, still in a Galilean way. In other words, constant speed, linear movement. So we suppose that the car, which is here, will move to the right, while the bullet and the light ray travel from A. Okay? Beam. This is funny. Now, what happened here? Well, first of all, the bullet speed viewed from inside the car is still the same. The guy inside the car has no way to know what's happening, and in any case, if he measures the bullet speed, it will still find the same value as before, which is b over d. Okay. Now, the bullet speed viewed from the Earth is now, by the definition we gave, is equal to c, because viewed from Earth, the bullet came from A to C, which is 0 to C. And the time, as defined, like we did before, is equal to E. Okay? And therefore, the speed viewed from the Earth would be C over E. And notice that instead of a bullet, if we send a light ray, then C will be equal to E, and therefore the speed of light will be equal to 1 again. So that means that it will be the same for any moving frame of reference, Galilean frame of reference. So using, just a definition, we derive, in a trivial way, the constant speed of light. Okay, so this is the slide that I added to the original video. The equivalence here between this new definition of time and the classical one is so trivial that I thought that it would be interesting to just take the example of the Lorentz law of velocity transformation, the rule of addition of speed. Okay, so here we get the usual formulas, except that c is equal to 1, of course. And then we can derive that v is equal to that. And that's because, c is equal to b plus ve, because the time for the car to go from b to c, is equal to the time for the bullet to go from a, which is 0, to c, which means e. So b is the length of the car at rest, and since it's moving relative to the ground, we need to apply the length contraction, and that's why we have a b over gamma here. Therefore, u2, is now equal to this, and then you replace that with that, and you get this. And if you apply, the Lorentz transform, then you get d equal to that, which implies that u2 is equal to this. And so finally, c over e is equal to v plus u prime 2 times this factor here, which means that c over e times this factor here is equal to that. And finally, that u2, which is equal to c over e, is equal to this value here, which corresponds exactly to the same formula as in the classical derivations in special relativity, assuming c is equal to 1. And it's good because that means that our definition is compatible with special relativity. So the conclusion will be the same. With this definition of time, we can derive the fact that light speed does not depend on the frame of reference, As opposed to, Einstein's procedure, we don't need clocks for that with our new definition. And we can still apply the same result, from the special relativity formulas, by simply using c equal to 1. And all of the above, of course, assume that we can precisely measure space, which is something that we did in a previous video, video number 2, when we redefined space. And finally, I'll restate, why we use light, to measure and define time like we did to redefine space. Well, that's because, it doesn't need a medium, it's isotropic, and also it's very fast and very precise, because you can go down to particle size because we use photons. And so, of course, we could use things like sonars, for instance, sound waves, to measure space and time. But it would be much, much less practical because of, in particular because of this, And also that, I got kind of a clue here because using Pauli's exclusion principle, which is not applicable to photons, that means the two photons can be at the same spot, the same position in space-time. And therefore, it cannot be more precise than this with matter particles like fermions. Okay, so that's our conclusion here. I hope you liked it and was not too boring. Take care and have fun always.